Hello, everyone. Welcome back. My name is Carolyn, and in this video, we are going to be talking about how to measure spread of data or locations of where a data value might be in regards to comparing it to somebody else. And so a couple of ways we can do that. First of all, we can kind of take our data and we can divide it into what we call our quartiles. And this is going to be able to, then we can kind of locate where a certain value is compared to everybody else. So quartiles, first of all, we have four, meaning we're going to take our data and divide it into four regions. To divide our data into four regions, we need three numbers. So we'll start with the median is going to be the middle value, and that's going to be our Q2, our second quartile. We will have a lower quartile, so that would be the middle of the bottom half of our data. And we're also going to have an upper quartile, Q3, which will be the middle of our upper half of the data. So the first thing we're going to do is just take our data, and I'm just going to kind of jump right in to dividing this into pieces. So the first thing we have to do is order the data. Now, this is some data that is basically considering, are you going to buy this thing or not? One would be, I would never buy this again, and 10 is I'm definitely going to buy this again. So I'm going to just order my data. So I have a 1, I have three ones actually, 1, 2, 3. I have a couple of 2s, 2, 3, 4 of them. I do not see any 3s. I do see a 4. I see a 5. Actually, I have 2 5s. I do not see any 6s. I see 2 7s. I see 1 8. Oops, there's another 7. Let me squeeze him in. Change that to a 7. Then my 8. And I have 1 2 3 4 9s. 1 2 3 4 9s, and then the number 10. Okay, so we're going to divide this into our quartiles. So we have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 data values. So I'm going to first find my middle. So 1 2 3 4 5 6 7 8 9. Here is my middle. So that's my median. It is also my second quartile. Now, when we divide this up, we do not include, if we have an actual middle value, we do not include it in our upper or lower data. So this was going to be our lower data from this guy down. This one will be our upper data from that point up. If we had had an even number of data values, so let's just say I had 6, my median would have been the average of those two. And that would have been my Q2, which would have been the median. And notice it would have been sitting smack dab in between those. So this is still going to be the bottom half, and this is the upper half. So our median really is not included in either of the upper or the lower halves. Either it's completely ignored or we have created it out of 2 other values. Okay, we're going to find Q1 and Q3 by finding the middle of the bottom or the middle of the upper half. So 1 2 3 4 5. We have to find the average between these two. Whoops, that's not right. 1 2 3 4. 1 2 3 4. It's right here, actually. So there is our middle value. So that is Q1. And here is my Q3, finding the middle of the upper piece. There are formulas out in Excel and Google Sheets that can do this for us. You just have to look for the quartile formulas. However, for this class, our data sets will be small enough that you will be able to do it by hand. So feel free to just do it by hand. And it's just to give you kind of a picture of where those values are. Kind of divides it up into 25% of our data is there, 25% is there, 25% of our data here, and 25% of our data is there. Okay, so thinking of where you're sitting, we a lot of times talk about this word percentile. If you've ever taken a standardized test of some sort and you get the results that says, I'm in the 85th percentile, or a child is growing and they have a height that is in the 37th percentile, knowing what that means. Well, the word percentile tells you the percentage of people or objects, if these aren't people, objects that are at your value or smaller. So the thing is to think they are at or below. So here or below. So if I'm thinking of finding the percentile, if I'm looking at my data here, granted, when we have small data sets, it's a little bit skewed. These answers aren't really great answers, but we're going to talk about the percentile rating of a 7. That means we got to figure out how many people would rate it at a 7 or lower. So I'm going to just count. So that would be my 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. Remember, we are counting the ones at or below you. So we had 13 out of the 19 that we had in our total group. And if you wanted to change that to a percentile, we would actually do that division. So 13 divided by 19, that gives me 0.684. And if you wanted to round to just the nearest percent, I'd say that this is the 68th percentile. If I do the same thing for the number 2, the percentile of a number 2, we'd have 1, 2, 3, 4, 5, 6, 7 people at or below a 2. So 7 out of the 19. So 7 divided by 19 is 0.368. If I'm going to the nearest per whole percentile, I'd say the 37th percentile. Okay. Sometimes we are looking for what value gives us a certain percent. And that's when that ogive comes in handy. So this was an ogive that I stole from our textbook. And I'm going to zoom in a little bit more here so you can read it. This is the perceived elapsed time, and this is our relative cumulative frequency. So that ogive that we learned how to read. And we want to know the 50th percentile. So basically, remembering this is people that are at or below you as we added them up, because we started with the small end and we kept adding. So we're going to take this 50, which is our percentage, and I'm going to go over to my graph. And this value here, so that 60, is my 50th percentile. That time is that 50th percentile. If I wanted to find the 70th percentile, same idea. Go over to 0.7. If I can draw straight lines. And it looks like we have a 70. It would be my 70th percentile. And that's kind of a way to show position. So if I'm in the 85th percentile, you know I'm in the upper part of the graph. If I'm in the 13th percentile, I'm in the lower part of the material. If I'm in the bottom 25%, middle 25%, we can talk about that. We can also talk about how spread out our data is. Let me zoom out a little bit here. Or how tightly compact our data is by looking at a couple of things. First of all, one real rough way to measure spread is to actually calculate the range. The range is your highest value minus your lowest value. It is a single number. We don't say, when we talk about things, we will sometimes say it ranges from 3 to 5. However, the range would have been 2 because it tells us how many data values do we go over, how many numerical values do we range from. Another one that's a little bit more detailed is something called the standard deviation. But in order to find our standard deviation, we first have to find our variance. The formula for this, and here's our formulas, okay, and we are going to be looking at a sample variance. Again, remembering sample variances, and we could also do a population variance. Our sample variance, we use S squared, and the square comes because we are going to be squaring these little things, and this is our formula. So kind of picking apart the formula, and we will go through one by hand, just so you can understand the pieces. This again tells us to add up. This little guy is my data value. Here is my X bar, which is my sample mean. And my N is my sample size. And we do subtract off 1. And then to get our standard deviation, our sample standard deviation, which is S, we just take the square root of this whole thing. Okay. When I go through the example, I'll kind of walk through these pieces so that hopefully they become a little bit more clear as to what we are doing and why we do it. So there are some statistics as well that we also can calculate these things on populations. Remember, this is going to be our population variance and our population standard deviation. When we do calculations on our population, we tend to use Greek letters. We use mu in the case of the mean. However, we're going to be using this symbol here, or that same thing squared. This symbol is also called sigma. This was called sigma as well. This one happens to be the uppercase. And this is our lowercase. So, but they are both sigma, and this is sigma squared. So we're going to be taking, and you'll also notice in the population, we divide by n instead of n minus 1. The reason for that is when we take a sample, a lot of times people will be, in our samples, tend to have less variance. They are less variable because there's something that kind of relates them all together to have caused them to become part of our sample. So that's why we like to overestimate a little bit of our sample standard deviation. Just would rather be a little bit on the larger side than the smaller side. My guess is it's probably somewhere in between those, but we'd like to err on being too big as opposed to being too small. So we're going to do one example by hand, and then I'm going to go finish these notes out. Yes. And then I'll also go to SALT at the end of this video to kind of show you how you can do this, or will be able to do this in SALT, which is the software that we have attached to our homework system. So what I do first of all is I'm going to kind of go vertically. when I write my data. So these guys, here's my data, my 75, my 80, my 85, my 90, and my 92. So these are my X's. Those are the little XI. So each of those is a data value. The first thing I'm going to need is to find my X bar. Remembering that X bar is your average. So I'm going to add those guys up. So 75 plus 80 plus 85 plus 90 plus 92. And that gives me 422, which I'm going to divide by 1, 2, 3, 4, 5. And I get 84.4. Okay. Now the formula says, going back up to my formula here, we're going to take my X and we're going to subtract off the mean. So I'm going to take my X and I'm going to subtract off my mean. If I were doing S on the previous page, it did say X bar. So I'm going to take 75 and I'm going to subtract off 84.4. I'm going to take 80, subtract off 84.4. I'm going to take 85, subtract off 84.4. I'm going to take 90, subtract off 84.4, and 92. I'm doing this to every single value. And I'm getting a result. Okay, when I take 75 and I subtract off 84.4, I'm going to get a negative number. And I get 9.4. This basically tells me that I am 9.4 units below, hence the negative, below the mean. The 80 is going to be a negative 4.4 units below the mean. If I take my 85 and subtract off 84.4, I'm going to just get 0.6 or 0.6 if you like the zero in front, which means I am 0.6 units above that average. I'm going to subtract the other two here and get those values. This is 5.6. And hopefully I didn't hit the wrong button. And this is 7.6. Okay, these values right here that we just calculated are sometimes referred to as the deviance, which is kind of like where the standard deviation comes from. So these deviants are deviating from the mean. It tells me how much they differ from the mean. This guy differs 4.4, and the negative tells me it's below. If you added these up, you will always get 0 because our deviants are spread evenly around the mean. Some are below, some are above, and when we add to get our mean, it's how it's calculated. So these will always add to 0. And what we are trying to do is get an average deviant kind of value. But if I add these together and always get 0, I can't really work with these numbers. So what we do is we take these values and we square them, because when I square a value, it is no longer negative, because a negative times a negative is a positive, and they all become positive. And I can also undo a squared, taking a square root. So that's why you will see this piece being squared, and then later to find our standard deviation, we then take its square root. Hence also the reason why we don't use just an absolute value, because we can't really undo an absolute value. So we are going to take all of these values and we're going to square them. So I'm going to take that negative 9.4 and square it. And remembering a negative times a negative does give me a positive. So I get 88.36. I square the negative 4.4, and I get 19.36. Squaring 0.6, I get 0.36. Squaring 5.6, I get 31.6. 0.36, and squaring 7.6, I get 57.76. And so there is them all being squared. So I'm going to kind of throw my formula up here. We have just done this inside piece. The next thing I want to do is this symbol, which tells me to add them all up. So I'm going to take these guys and I'm going to add them up. And that's going to give me the sum of these xi minus x bar squares. So I'm going to take that, all those numbers, adding them. Oops, shoot. There we go. And I get 197.2. Okay, I'm just going to double check that real quick. Because I don't want to screw up too badly. All right. And then since we're talking about a sample, we are going to divide by our n minus 1. Now, n is the number in our sample, how many things we had. And we had 1, 2, 3, 4, 5. So we're going to take this number and divide by 5 minus 1. Or we're going to take 197.2 and divide it by 4. So I'm going to take that divided by 4, and I get 49.3. This is S squared, which is my sample variance. If I want my sample standard deviation, I'm going to take the square root of this number. So using my calculator, so I have my 49.3 in there, my square root button is kind of above the x squared, so that I have to do a second function and then hit that button. You'll see my square root come in here. I also have this little A and S key, which allows me to take my number from before. So all it's doing is it's taking this 49.3 and putting it into that spot, or I could have typed it in. And then I'm going to hit my enter button. And I get 7.02. And then I would follow the directions of whatever the assignment said to round, however I needed to round. So I'm just rounding to 2 decimals. So this is a long drawn out process, but you can kind of, by going through this, it kind of shows you how we get an average of how far apart these things are. So we are taking how far away those data values are from the mean. We get these numbers, but if I added them and divided by a number, I can't do that because I always get 0. So we square them. And at some point we take a square root again. So it's kind of like undoing what we did. The larger the value we get, the more spread out your data is going to be. The smaller your data is, the more closely tight, compact the values are. And we'll see how that plays a role in the shape of our data in later chapters. The last thing we're going to do, and these kind of go together, is we're going to calculate something we call that inner quartile range. It's another way of measuring how spread out your data is. And the way the definition or the formula for that inner quartile range is to take our Q3, remember that median of the upper half of our data, and subtract off the median of our lower half of our data. And we've already did an example finding Q1 and Q3. So our inner quartile range is taking those two values and simply multiplying them together. The reason we like this one is because it is not going to be affected by really large numbers or really small numbers. Standard deviation, which we just calculated, is greatly affected by those values because if we have large values or small values, first of all, they're going to affect our mean. And since we use the mean in the calculations of standard deviation and variance, they will also be greatly affected by large values and small values. So this inner quartile range is a good representation of kind of the spread of our data because it doesn't take into consideration those really big, large numbers or really small numbers. So we're going to do just an example, and then I'm going to be using this to do some determinations in a little bit. So going to first of all find my Q1 and my Q3, and I'm going to order my data. So my 43 is the smallest here. Then I'm jumping up to, it looks like a 70, a 75, and we have a 78. I have an 80, an 85, and then an 88. I have a 90, a 92, and a 95. And I probably should have written them a little bit better. Okay. Well, we're going to find our Q1 and our Q3. But in order to do that, I need my second quartile as well. The second quartile is going to be the middle of these values. We have 10 scores. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So our middle would be the average of these two, since I don't have a true middle value. I add those two and divide by 2, I'm going to get 82.5. So that would have been Q2, or the median. And it also kind of divides into our lower half and our upper half of our data. The lower half, the middle value, is right there, Q1. And in our upper data, there is our Q3. So our inner quartile range, IQR, is taking that Q3 and subtracting off Q1. So taking our 90 minus the 75, which gives me 15. So it's kind of telling me I have a spread of 15 units in that middle section. So it's kind of like the middle 50%. Because if you remember, 25% of our data will be here, 25% of our data will be there, 25% and 25%. So between these two, it's roughly the middle 50%. Using this value, we also use it to help us determine if something is too big or too small. Is it truly an outlier? So for example, this 43 is a little bit below everybody else, but is it an outlier? Is it far enough from the data to be considered an outlier? To find these outliers, what we're going to do is we're going to find some sort of boundaries as to a safe zone, so to speak. So if you are within these boundaries, you are not considered an outlier. If you are outside these boundaries, we would be considered an outlier. The formula for it is finding that taking our Q1, and that's our lower guy, and then we're going to go down a little bit, and the amount we go down is 1.5 times that inner quartile range. We also find an upper boundary by taking our Q3 and going up some. So we go up that 1.5 times that inner quartile range. So you're going to, our Q1 and our Q3 map out our middle 50%. Then we're going to go down a little bit to trying to make sure which way I want to go. This would be down for you guys. Down a little bit to get a lower boundary and up a little bit to get an inner boundary. If we're inside there, we're okay. Outside, we're considered outliers. And we're going to do that for these problems. So we're going to take our Q1, so our lower boundary value is taking that Q1 and subtracting 1.5 times the inner quartile range. So our Q1 was at 75. and our inner quartile range we had found to be 15. Now, the thing to remember when I'm doing this is order of operations, and order of operations tells me I'm going to multiply first. So I'm going to take that 1.5 times my 15 first before I subtract. And I get 22.5. So I'm going to take 22.5 away from 75, and I get 52.5. So this is my lower bound. Anything smaller than it would be considered an outlier. So this tells me that 43 is an outlier. Okay, we're going to do the same thing on the upper side. We're going to take and find our upper boundary. I don't believe we will have any outliers, but we never know. To do this, we're going to take that Q3 and we're going to add 1.5 times the inner quartile range. So we're going to take our Q3, which was 90, and we're going to add 1.5 times the 15. Again, remember, you multiply before you add. So we're going to take our 90 plus the 22.5 that we had, which is 112.5. And we do not have any values that are larger than this, so we have no upper outliers. Sometimes we could also say that 43 is a lower outlier or a small outlier. And different textbooks will have you classify things slightly different. Okay. Using all of this information, we can also kind of make a picture of what we've kind of gotten with the Q1s, the Q2s, the Q3s, boundaries and outliers and so forth. When we do that, what we can create is something called a box plot. So a box plot is going to use those pieces that we talked about to create a picture of what this is. They basically will use this 5-number summary that we talk about. I think it's a little bit different than that because we sometimes use our smallest value and our largest value, but we also will use the smallest value that is not, or largest value that is not outliers. That are not outliers. And then we also use any outliers that are in there. This has changed over the years because statistics is a relatively new branch of science. And when it first came out, we really didn't have a way to measure if something was an outlier or not. And now this formula has come out within the last, 20 to 30 years. And so now the change in the box plot is also coming around as well. So the 5-number summary is a little bit more detailed than just your smallest value, Q1, Q2, Q3, and your largest value. It's technically your smallest value inside the boundaries, Q1, Q2, Q3, your largest value inside the boundaries, and then any outliers that you might have. So sometimes these box and whiskers are all These box plots are also referred to as a box and whisker because of how it's constructed. So I'm gonna construct one for these 10 test scores. So like every graph, we should have a good title. So here's my good title. Although my good title should say something like exam scores of some sort. Okay, then what I'm going to do is I'm going to have a scale that goes this direction, or you could do these vertically. I've seen box plots done vertically as well. And our data ranged from, our lowest value was a 43. I kind of brought my data here all the way up to a 95. I think what I'm going to do is write the word scores down here. And I think what I'll do is count by 5. So I'll go 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, and 95. And if I wanted to, I could put the 100 in there. So those are my scores. Okay. First thing I do when I'm creating my box and whisker is to create the box. And the box is calculated by finding your median, which for us, it was an 82.5. So that is going to be right here. So I'm going to put an up and down line. I'm also going to put one where there's at Q1 and at Q3. So Q1 was there and Q3 is here. And this is going to create the box for the box plot. Then what we do is we draw a whisker, which is going to go from our box to the highest and lowest values that are within our boundary. So if you remember, our upper boundary was 112. The 95 was our largest value. So I'm going to put a dot for 95 and draw a whisker to it. On the other end, 43 was an outlier. So our largest value or smallest value that's still within the boundaries is that 70. So I'm going to draw a whisker to that value. Then what you will see is your outliers will be designated using, some textbooks use dots, other textbooks use stars. So that 43 will get its own little dot. And by having it broken off, tells the reader that this is an outlier. Other textbooks might use a star instead of the dot. It really depends on what you want to do. But a lot of them are now using the box and the whiskers are going to be within our boundaries, and any outliers are going to be broken off from that box and whisker plot. We can then also interpret our data to kind of see if we have some symmetry going on. If you see outliers, remembering those are going to skew things down. So this 43 is going to skew things to the left or negatively skew things. So we can kind of see some of the ideas here. You will see symmetry if everything kind of looks even, and that median is the middle of your box. So we do have a little bit of symmetry going up in here. This thing kind of throws things off. If you have whiskers, or just imagine the whisker going all the way down, that left whisker would have been a lot further than the right whisker, so it's skewed to the left. Or if you have outliers, that will help skew things. Similarly, if I had outliers up here, it might have skewed things to the right. If you have, here's a couple more pieces here. So outliers, you can see we have outliers here and here. We have another outlier here as well. You can also do, you had two pieces of data and you were going to compare them, again, like we've done with box, not box plots, but dot plots. And we also saw it with bar graphs. And you're going to compare two sets. You're going to want to make sure to have equal one data set, one line. So we'll have one scale and we'd have both boxes, one on top of the other. So just kind of keep that in mind if you're doing comparative box plots. You want to use one set of axes so that you can compare the two. This concludes our graphing section. And the mean, median, mode, and graphing. We're going to go into a little bit more technical stats from here, but I do want to, before I end this video, I want to go and share with you a little bit in SALT. So when you're doing the homework and you see this SALT button, you'll know what it does. And I hope that this takes me where I want to go. So we'll see what happens. But you'll see these little salt buttons pop up. And what it's going to do is if you hit this button, so I'm clicking on it. So it's telling me my data is being transferred into WebAssign. And what it has done is it put all of my data in here for me. So there's my data. The nice thing is it also allows me to then quickly get at any information about this data. And all of that information is going to be held in this descriptive statistics button. So instead of trying and taking it to a spreadsheet, it will automatically do all the work for you. So if I clicked on this piece here, there is the mean of our data, so 81.85. There's the standard deviation already calculated for me. The minimum value, the maximum value, there's Q1, there's Q3, and there's my maximum value. And I think I can probably scroll up and there might be a few more things located. But I don't have to go and calculate anything more. I could, if I wanted to, get a few more pieces. So it can also do that as well. I also have charts and graphs that it can draw for me. It can draw a box plot. Make sure I select which variable I want to do. So if I wanted to create my box plot, there's my box plot. I could do a scatter plot, dot plots, whatever kind of plot I wanted to. Also with that data can be done rather quickly using SALT. So the things that we've learned can be done in this system as well. And the nice thing is it is linked right to our homework. And when you click that button, the data from that question goes directly into our system here. So hopefully you'll get to play with this a little bit more as the semester goes on. If you have any questions, please ask and we can talk about it. Until then, I will see you in the next video. Have a great day.